Welcome to lecture 8. Let's do a few more examples. So you can recall that earlier we had just started doing homogeneous deformation, right? So this is the deformation in which the deformation gradient is constant, and therefore we can write y is equal to a constant f into x, right? And one of the example of f naught that we took was triaxial stretching, lambda 1 e1 tensor product e1 plus lambda 2 e2 tensor product e2 plus lambda 3 e3 tensor product e3. Okay, so and depending on lambda 1, lambda 2, lambda 3, you can have stretching or compression in the three directions. Lambda 1 greater than 1, so lambdas greater than 1 corresponds to stretching, and lambda less than 1 corresponds to compression. Okay, so you saw that the three material line elements along the axis E1, E2, and E3, they underwent pure stretching. Okay, so if I draw the picture, then this is how it looked like. So if it is lambda 1, then lambda 2 and lambda 3. So you can see this, and from the picture what you see is that lambda 1 and lambda 2 are greater than 1 and lambda 3 is less than 1. Therefore, there is a compression in the E3 direction. Also, you see that the angle between these perpendicular line elements do not change. It remains as it was earlier. And you may recall that this angle between two perpendicular line elements is used to denote shear. Right? From your undergraduate course, you can recall that it denotes shear. If it is, the deviation from 90 degree, that is shear. But here there is no deviation, so there is no shear in this E1, E2 plane. But that doesn't mean that none of the line elements are undergoing shear here. In fact, if you can think of a tilted, let's say this main diagonal, a line element along the main diagonal, so suddenly its orientation has changed, isn't it? The angle that it was making here, it's not the same over here. So the orientation of the line elements, this red line element has changed, whereas the orientation of the line element along E1, E2, E3 has not changed. Okay, so I can just make a remark here. It's not changed, whereas the one along main diagonal changes. Okay, now let's further specialize this deformation and say that lambda 2 is equal to lambda 3 is equal to 1. So in that case, your f naught is simply lambda 1 times E1 tensor product E1 plus E2 tensor product E2 plus E3 tensor product E3. Okay, and this you can write in slightly different way as follows. So I'll say it is EI tensor product EI with a summation over I plus lambda 1 minus 1 of E1 tensor product E1. I hope you guys can agree with me. And this first one, that's also the tensor notation for identity tensor. No, identity tensor to which whatever vector you multiply, you get back the same vector. So that's the definition of identity tensor. No, it gives you back the same thing, and its matrix form is unity matrix, right? Matrix with one on the diagonal. So this is a matrix form. So matrix form has one on the diagonal, and off diagonal are all zero. So what you see is that this is looking like I plus lambda 1 minus 1 E1 tensor product E1. So this is also called uniaxial stretching. Okay, so this is called uniaxial stretching, and this is different than what is called uniaxial loading. It is different than uniaxial loading. I think most of you may have heard about this uniaxial loading. Can anyone tell me why it is different? Anybody? So Deepsika is asking, please elaborate the second step of lambda 2 and 3 equal to 1. So I have just taken it to be so. You can't ask why it is so. I have just taken a deformation in which they are equal to 1. Somehow, if you can do such a deformation. Okay, so second step, sir, F naught. Oh, even here, second step here. Okay, so this is see what I did is this lambda 1 E1 tensor product E1. I can write as E1 tensor product E1 plus lambda 1 minus 1 E1 tensor product E1. So this thing is E1 tensor product E1 plus lambda 1 minus 1 E1 tensor product E1. Right? When you add these two, you get what it is there. And then I come back here. Okay, so as many of you have written also, this uniaxial stretching is indeed different than uniaxial loading. So uniaxial loading, it's more physical, where you may have a specimen. It could be in the form of beam or in the form of, let's say, a plate, thin plate, and you may be applying force like this here in one direction, and when you pull it, then due to Poisson's effect, the stretching in the lateral direction is not one, right? There's some contraction in the lateral direction. So therefore, this is the case of uniaxial loading. So I'm talking about load being applied in one direction. So as the lateral directions do not have lambda equal to 1, therefore it does not correspond to uniaxial stretching. Okay, uniaxial stretching is, I would say it's more difficult to attain. Somehow you have to constrain the body so that it does not contract in the lateral direction due to Poisson's effect. Okay, but theoretically you can think of such a deformation. All right. Similarly, you have biaxial loading. So these days people do uniaxial loading as well as biaxial loading. There are sophisticated equipments which can do biaxial loading. So there again, you can apply load in two directions in a controlled manner. Okay. So just think of again this plate, and you may be applying force like this. So this is, let's say, P1 and this is P2. So this is biaxial loading where P1, P2 can be independently varied. But the one along P3, sorry, the P3 is 0 here. That doesn't mean that lambda 3 is 0. Sorry, lambda 3 is 1. So this does not mean that lambda 3 is equal to 1 here. So this is the example of biaxial loading. And lambda 3 is not equal to 1. Okay. So, and this uniaxial stretching, this form that you have here, it says that you are stretching in the E1 direction, isn't it? You can likewise think of a more general uniaxial stretching, a general uniaxial stretching, where this F naught will be equal to identity plus some lambda minus 1 into a vector n tensor product n, where n is a unit vector denoting the direction. So this is again uniaxial stretching, but in the direction n, along the direction n. What you had earlier was the uniaxial stretching along E1 direction. This is along the direction n. Okay, along n. Likewise, you can also think of shear. So shear deformation. So I think all of you may have seen this picture where you have this body and after deformation it becomes like this, right? Let us say this is some angle, um, say this is K, and it is E1 and this is E2. So if you try to write down the formula for the deformed coordinates in terms of undeformed, then suddenly you know that y3 is same as x3, right? In the third direction there is no displacement, so y3 is equal to x3. Then what can you say about y2? Y2 is equal to, anybody? Is the second coordinate changing after deformation? So as you can see here, it is not changing. So y2 is also equal to x2. But for y3, sorry, y1. So that is equal to x1, the original, plus this extra displacement, which is proportional to the x2 coordinate, k times x2, isn't it? And this is an example of shear deformation, because you can see that the original angle, this one which was 90 degree, has finally changed and it is less than 90 degree. And this is the map for the shear deformation. So um, let us try to write this in tensor form. So I believe we can write this as y is equal to identity times x. You see, identity times x, this takes care of this part over here, but then you have this extra term. So how do I include that extra term? So anybody has idea how can I include this extra term? K e2 tensor product e2 into x. So I think you guys are getting close. This is not correct anyway. So e2 tensor product e2. Well, you just saw a verb that when you have n tensor product n, it's corresponding to uniaxial stretching. But what we have here is an example of shear. So this actually turns out to be k times e1 tensor product e2 into x. Let's see why it is so. Um, so inside the bracket you have a second order tensor, rank 1 tensor multiplied with x. So how does this work? You have to do e1 and then these two have to be dotted. That's the way this multiplication works. So it is x dot e2. So what is x dot e2? That's x2, right? So what you have is k x2 e1, and this is what you want. You see, you want kx2, but in the e1 direction, and therefore you have here kx2 e1. Okay. So of course, one of you wrote e1 cross product e1, that is 0. So anyway, so we can now come back here and write it as k times e1 tensor product e2 into x. And this can then be, if you take x as common, it is I plus k e1 tensor product e2, then the whole thing multiplied with x. So this deformation gradient, this corresponds to shear deformation. And because you know what kind of deformation is this, you can now see what is E2. E2 is the planes which are undergoing shear. E1 is the direction of displacement due to shear. Right? You can see here the displacement is extra displacement is happening in E1 direction. And it's the planes whose normal is E2. They are undergoing relative shearing. So let me make that clear to you here. So if you think of these planes, um, See, these are set of parallel planes whose normal is along E2, and they are getting displaced along E1 direction. Okay, so these set of parallel planes, they are getting displaced in the E1 direction. So relative, if you look at two planes which are just next to each other, two sets of parallel planes next to each other, they are undergoing shear in the E1 direction. So you'll call this shear, right? Because the displacement is such that it is perpendicular to E2, the plane normal. So what you see here is that this deformation is corresponding to, when you write it in tensor form, then E2 is telling you the plane normal, the planes which are undergoing shear, and E1 is telling you the direction of shear. Okay, so I can now make that remark. So E2 are the normal to parallel planes which undergo shear, and E1 is the direction of shear displacement. Okay, and what you see is that they have to be perpendicular to each other, then only it is shear. If they are parallel, then it corresponds to uniaxial stretching, right, which you saw just now above. And if they are perpendicular, it corresponds to shear. Okay, so having seen that, for a general shear deformation can be written as follows. So that will be identity plus K into M tensor product N, where M is perpendicular to N. And then you know which is what. So this, for example, is normal to parallel planes which undergo shear. The second one, right? And the first one is the direction of shear displacement. I hope that this is clear to you. So these are, two simplest deformations: uniaxial stretching or shear deformation. And then you can also compose them together. For example, you can think of an F. So if I call this Fs, S for shear, well, stretching is also S, so maybe SH, and this is then ST for stretching. Then you can also have a deformation which are product of the two. Okay, you can have F equal to FSH into FST, or FST into FSH, and then you might want to see what is it actually corresponding to. You should work it out and see what does this correspond to. Okay, any questions so far? What is the physical significance of lambda equal to 1? Um, so you mean for the case of pure stretching deformation? There you saw that lambda is corresponding to stretch. So lambda not equal to 1 corresponds to the case where there is neither stretching nor shear. If lambda is greater than 1, it corresponds to stretching because the length is increasing, and if lambda is less than 1, then it is corresponding to compression, right? So that's the physical significance. And for the people who are in fluid mechanics, So you always come across the shear flow. So what will you do in that case? How can you change this deformation so that you make it shear flow? Anyone who likes fluid mechanics, can you tell me what should I do here to make it a shear flow? So you simply make K as a function of time, the amount of shear that is changing with time, right? So if you do that, then the shear will keep on increasing, and shear rate is then K dot. K make it as a function of time, and K dot is the shear rate. Okay. So if you do it Kt, it corresponds to shear flow, and K dot is actually shear rate. Okay. Okay, so having seen these simple deformations, now we want to find out formulas for length change or change in orientation. So the question is, we actually want to find the formula for strains for the case of general deformation. Let's say that. So formula for strains for general deformation, and by general I mean large deformation. In your UG class, for example, you have seen that epsilon xx is equal to del ux by del x, isn't it? Likewise, you must have seen that gamma xy, the shear strain, is del ux by del y plus del uy by del x, right? And then you can talk of shear rate also. So, these formulas, by the way, they hold only when the deformation is very, very small. So we had neglected higher order terms there while deriving that in the undergraduate class. But now we want to have a more general formula which works for not just a small deformation but also for large deformation. Okay, because you can have soft materials which, for example, can bend like anything. If you have a rubber tube, for example, if you have a beam and that's a rubber tube, you can actually bend it like this, right? You can do anything to a soft material, and they have several applications these days. So it is important to know what will be the formula for strains when your deformation is large. So let us try to obtain that. So again, think of this reference body which is getting deformed into this current deformed shape, and it is induced through this deformation map y hat of x. Okay, and and then you know that the line elements, small line elements, infinitesimal line elements dy are related through the deformation gradient times dx, where this f has to be evaluated at the point where you want to see the change, at point of interest. Okay, so basically if you are at a point x here, and then here you are at a point y, and then you have a very small line element, and that is getting deformed here. So it's becoming dy, here it was dx. So when this line element deforms, not just its length is changing, its orientation also changes, right? And it depends on your f at that point. So we can make this remark, not just length, but also the orientation of the line element changes. So this is the local picture that we have derived, how they are related, very infinitesimal line elements. Now let us ask this question, all of us ask ourselves, if somebody asks me for this general deformation, what will be, for example, longitudinal strain in the body? What will be the longitudinal strain in the body? So how can we answer this? Anybody? What do you think? How should we tackle this problem? Yeah? So I'm sure many of you are thinking, how do I define this longitudinal strain in the body? The simplest picture that we have seen is you have a bar, and then you might be stretching it along the axis, and then we say that longitudinal strain is simply delta L by L, right? So this is a very simple picture or simple example. But here we don't have any bar. You see, the body is an arbitrary body. So how do I measure longitudinal strain in this body? Or even, is it good to ask this question, what is the longitudinal strain? Should you be measuring the change in length of the body in this direction, or in this direction, or in this direction? What should we do to find the longitudinal strain? Anyone? Strain energy. See, I'm not talking about energy here. I want to have the formula for strain. So I think we should not involve energy or force. It's a purely kinematic question. We have to answer this based on the knowledge of deformation of the body. Using the information of this map y hat, can we answer this question? So that's a purely kinematic question. Take the direction in which deformation is highest. When you say deformation, do you mean that the change of length is highest? But why should you do that? Because you know about, um, for example, this case of a beam, and you are undergoing this uniaxial loading, then you have the concept of not just longitudinal strain, but you also have the concept of lateral strain. You have both the strains there. So longitudinal strain is like the direct strain, and lateral strain is the one perpendicular to it. So you are not content with just getting the strain in one direction, right? Strain along the longitudinal axis. But what is a longitudinal axis here? For this arbitrary body, which one is the longitudinal axis? Yeah. dy hat by dx is equal to F deformation tensor strain along the applied force. Okay, but what if suppose you are applying distributed load on this beam? There's no one direction. Then so obviously, so these are very good questions that is coming to your mind, that if it's a general body undergoing arbitrary deformation, then what should be the concept of longitudinal strain? Strain along the longest length. That's again why you want to just measure strain along longest length. Just you saw in this case of beam, the lateral strain is also a longitudinal strain. There are two kinds of strain: normal strain, shear strain, or longitudinal strain. So lateral strain is also kind of changing length by length. The one that is, of course, used, which is also quite natural, and it is motivated by this simple picture here. For a case of beam undergoing uniaxial loading, then you say that longitudinal strain is change in length by length. So that's what we try to find for a general 3D body. So you have this general body, and you see there's nothing like a bar here. But what you have is, those material line elements, right? At You have these material line elements in the body. Even at a point, you have so many line elements passing through that point, isn't it? So we have infinite material line elements in the body, and even at a point there are infinite line elements, right? So maybe a very natural thing to do would be, why don't we measure the change in length of these line elements? If you can measure the change in length for each of these line elements, then it will correspond to longitudinal strain of those line elements. So now, instead of asking the longitudinal strain of the entire body, you have to say in terms of longitudinal strain of line elements in the body. So there is no one single longitudinal strain for the body. There are so many longitudinal strains corresponding to different line elements. Okay, so so this is a natural thing, isn't it? Here, what you have to just measure is the change in length of those line elements, right? So, so now the question is, when we say of longitudinal strain, then what is coming out of the discussion is that longitudinal strain is different at different point. So it's a local concept now. Okay, it's different at different point. There is no single longitudinal strain. not just this, even at a point, longitudinal strain could depend on the orientation of the line element. Okay. So obviously the next question now is, if this is how we are measuring longitudinal strain, I hope all of you are comfortable with this definition. So these line elements are like a tiny bars that we had in the simple experiment. Okay. So the line elements, they are like the tiny bars whose whose length change you are trying to measure. Okay, so now let's try to find out the formula for this longitudinal strain. So just like I told you, we have to pick a line element in the body. So suppose I pick a line element here. It will be good to pick a line element which has finite length. That means its tail is at x and the head is at x plus delta x. Okay, so it's a line element of finite length. So Shubham is asking, in shear also will there be longitudinal strain? So we'll just derive the formula and it can actually happen. You'll see that it's possible. And I can show you a very clear example here, which we already have that picture. Think of this line element along E2 direction. Okay. What is its final length? The final length is this tilted line, right? That's the tilted line is the final length. Isn't that greater than the original length? So although this is an example of simple shear deformation, but still what you see is that the line elements along E2, they are undergoing change in length. Okay, and therefore there is some longitudinal strain for line elements along E2. Of course, if you use the undergraduate concept of longitudinal strain, then epsilon yy will be del uy by del y, right? And uy, the displacement in the y direction is 0 here. So you'll find that it is 0. So you can see that the undergraduate formula is obviously approximate. It is not giving you the actual change in length. Okay, so in this course, like I told you, we are going to derive the change in length which will hold for large deformation. So here also, if you let k go to 0, no, then you will see that the change in length is indeed to the linear order, it is 0. So we'll see all those things later on. Okay, so but very good that you pointed this out. So somebody is saying in E1 also they are undergoing change. So of course in E1 there is no change in length. Look at this line element, for example, it remains same. This line element, for example, the line element along E1, and this is changing to this one, no? So the length is the same. So this is a example where the longitudinal strain in E1 direction is 0, and this you will see not just from the undergraduate formula but also from the more, the exact formula that we will derive in this class. Okay.
shear case which you have discussed here.
Yeah.
So it is a small shear case or a generalized case of shear strain.
So I should say it's a general shear deformation where K can be small or large. Okay.
So if suppose the K is large, so I want
Yeah.
to ask the line element which is above, means the second line element which is horizontal,
Yeah.
will it not come somewhat downward?
Well, no, because you see, as per this formula, so we are already prescribing this. You are thinking of from the physics perspective, but here the kinematics is prescribed. This is what is happening. Okay. So you see here the y2 is equal to x2. So it's not going upward or downward.
Yes, sir, from this perspective it will not come, but if we see in practical cases, uh,
Yeah, in practical cases, if you are thinking that I'm applying shear by applying some load here, some shear load, then of course the even you will even have displacement in the second direction. When you undergo finite deformation, then you will have displacement in the second direction also.
so in the shear strain,
Hmm.
we will consider this displacement in the second direction or not for finite deformation.
Well, we'll see that. What is the see? You have to ask what is the formula for shear strain.
Yes, sir. It is
Just like
related to change
we
in the
saw
time.
for the longitudinal strain, we saw that what we are saying is that it is varying from point to point, and even at a point, you are asking which line element, the orientation of the line element. So similarly, when we talk of shear in the whole picture, we first have to define what is shear strain, and then only we can ask the question now. But it is, of course, it won't be completely different than what is our intuition about it. Only the same change in angle between two line elements. Okay.
Okay, sir.
But Rahman ने क्वेश्चन पूछा है कि as this is the exact formula for the deformation, I mean we haven't yet found out, but we want to find that. Is there still some error if we measure the deformation or strain in the practical body with the formula and with some strain instrument like a strain gauge? So how much error it will give? So these are very good questions. जैसे स्ट्रेन गेज क्या करता है, वो तुम्हें उसमें दो पॉइंट रहते हैं और उसके बीच का चेंज इन लेंथ वो बताता है. So we'll discuss all these things, as we when we finally derive the formula, we'll also talk about this question. It's a very good question.
So in a body, at every point we have infinite number of line elements.
Hmm.
It's infinite number of small element dx. So
Correct. Correct.
deformation of each and every will be different depending upon the orientation.
Yes.
So how can we say this or support?
क्योंकि तुम्हें देखो जैसे कि सिंपल केस में बार के लिए जो बार को हम लोग स्ट्रेच करते हैं तो वहाँ तो तुम्हें दिखता ही है. मैं नीचे कहीं कर रहा था ना, हाँ यहाँ पर जब स्ट्रेच करते हैं तो इस डायरेक्शन में जो लाइन एलिमेंट है उसका लेंथ कुछ और तरीके से चेंज होता है और इस डायरेक्शन में जो रहता है उसका कुछ और चेंज होता है. राइट, इसलिए तो लैटरल स्ट्रेन और लॉन्गिट्यूडनल स्ट्रेन अलग अलग होते हैं.
So sir, we are saying on the basis of that, or after this we can prove it also by some way by with the help of the formula or by calculating in two different directions.
फिर से बोलो, टू व्हाट?
Means with the help of this cylinder that you have explained above.
या.
So we are with that we are saying for this with for this body which is having no shape, or with the formula after we can say it also by getting the value
Yeah,
means
that's a
in two
very good.
different directions.
That's a good remark. Indeed, once the formula comes out, you will see that the formula has the orientation also in it. If you change the orientation, you get different longitudinal string.
So we'll have a component of orientation in the formula.
Yes, exactly.
Okay, sir.